Hello again, this is the Pencrest High School AP Physics C video series. This is video 1C, integrals with respect to time. Now, you'll recognize the progression again. When we go down the progression, we use the derivative or the slope. Last year when we went up the progression from acceleration to velocity to position, we used the area under the curve. It was usually a pretty cumbersome process with lots of different shapes. We had squares and rectangles and triangles that we had to find the area for. So now we're going to use a different process, again, that's a little more precise. We're going to use a process called integration. Again, we've added the jerk term below acceleration. As we go up the progression, we use a process called integration, which is effectively the opposite or the inverse of doing the derivative. So here's the general form for the integral of a polynomial function. If we have our y equals some constant a times t to the n, when we integrate with respect to time, this is an integral symbol. We're going to integrate the function y times dt. Again, this d is not a variable, it's a very small delta. And what we're going to get is, again, we carry the a. We're going to leave it here, times t to the n plus 1. N plus 1 is an increase in the exponent, and then we're going to divide the whole thing by the n plus 1. So this is the operation. So think t to the n plus 1 over n plus 1. And then we're going to have what we call an integration constant. You might remember from doing derivatives that constant terms go away when you do a derivative, because there's no t term on them. When we're going the opposite way, when we're doing an integration, there may be a constant there. We don't know. We'll typically have to use initial conditions or something to that effect to figure out what the integration constant is. So again, instead of going down the ladder and decreasing the exponent, we're going up and increasing the exponent. If we look at the generic velocity formula as a function of time, v equals v naught plus a naught t plus 1/2 jt squared. J is the jerk, of course. When we integrate v with respect to t, we have the constant term v naught times t to the 0 plus 1 divided by 1 plus a naught t to the 1 more, which is 2, divided by 2, plus 1/2, we're going to have j t to the third divided by 3. There's already a 1/2 here, so 2 times 3 gives us the 6 down here, plus the integration constant c. Now we'll clean it up a little bit, and we end up with what is effectively the generic position formula. The integral of v dt gives us the position. We have v naught times t plus 1/2 a naught t squared. This should be pretty familiar. Plus the new 1/6 jt cubed term plus c. You know, in the generic position formula, we have an x naught. So that x naught, the initial position which you're frequently given, that's the constant of integration. So your x naught, your initial position, would be the c here. Okay, that's it for integration. Again, using the power rule is pretty simple and straightforward. Next up, we're going to look at some quantification of kinematics with jerk. We're going to look at the generalized formulas for position, velocity, and acceleration, and use them to calculate particular quantities and so on. And then we'll move on to graphical interpretation and quantification. All right. Until then, enjoy, and I'll see you again next time.